Okay, we start our new unit, Unit 3A. Unit 3 is a big unit. It is broken down into 5 or 6 sections. So we have Unit 3A, B, C, D, and E, I believe. So this unit takes us to the end of the year. However, again, it's just a very large unit. Okay. And it covers a lot. So what we're starting off with here are exponentials with natural base. So we've talked about exponentials and natural base in Unit 2B, and we expressed that it meant that our base is the irrational number e. Okay, e is a number just like pi. So we're going to dive into a little deeper about what e looks like. So we're going to find e. You're not writing this down, we're just talking about it. So if you look right here at this table, this is how the number e came to life. So some really bored mathematician or just super smart, they didn't have screen time back then, so they had to keep themselves busy. They realized that there's a pattern that every time you are adding on or taking the power, the numbers are approaching something, and the numbers that was approaching was 2.718. 281827. That's what it was steadily approaching, and it just keeps getting closer and closer to that. Okay. After doing that, they realized, okay, what are we going to call this? And they decided to call this number E. Where'd my pen go? E. Okay. So when we are analyzing y equals e to the x, we are analyzing approximately e is approximately 2.718. Okay. And we're going to talk about this as a function. It has the same attributes as any other exponential function. The only difference is that it's e. Okay. So you still have a graph that is increasing from left to right. You still have the y-intercept of 0, 1 for the parent function, and everything else still upholds, stays the same. All right. So let's talk about the attributes. Our first exponential model here is called a growth. So we're going to call this our growth model. For the growth model, our domain interval is going to be from negative infinity to positive infinity, because from left to right, our graph continues forever. Okay. Our range, however, has a restriction. It has a boundary line at 0, right? It does not go below 0. So our range, which is from bottom to top, starts at 0 and continues to infinity. Okay. Because we never get to 0, we have no x-intercept, and we only have one y, I can't talk, a y-intercept at 1. So our y-intercept is at 0, 1. Okay. That boundary line is called a horizontal asymptote. Your horizontal asymptote is on the x-axis at y equals 0. Okay. Your function is approaching this as x goes to negative infinity. So as you head to the graph towards the left, so as you go to the left of the graph, you can see that it's getting closer and closer and closer to 0. Okay. So overall, we would say that this function is increasing from left to right. It's a one-to-one function, means that no x values repeat and no y values repeat, meaning that it passes the vertical line test and the horizontal line test. It is smooth and continuous, so I can take my finger, trace along it, and there's no gaps or holes in my graph. Okay, what is the opposite of a growth model? Anybody? Everybody? Hmm? A decay model. So this is our decay model. The decay model is when your base is between 0 and 1. Everything's going to be the same except two factors. Factor number 1 is that your range is still, oh, not factor number 1. Factor number 1 is that it is decreasing from left to right, and that your A value obviously is a fraction, because instead of you gaining, you are losing rapidly. Okay. Because of this decline, our horizontal asymptote is x-axis. It happens, we're going to approach it coming from the towards the right. And I made a typo in your notes, and it should say decreasing, not increasing. So please correct that. It is still a one-to-one function because it passes the vertical line test and horizontal line test, meaning that no repeating x values and no repeating y values. And it is smooth and continuous. Yep. Well, as it's approaching the asymptote, where it's getting to zero. Yep. All right, questions about our basic attributes of the parent function. Cool. So now we're going to talk about the transformation rules. Oh, sorry. Before we talk transformation, at the bottom, just wanted to make clear that if the bases are the same, that means that the two powers have to equal each other. So if your bases are the same, then the two powers have to be equal. So if I know u, then I can solve for v, right? Or if I know what v is, I can solve for u. Okay. Our exponential transformation. So our exponential transformation applies to all exponential functions, but in particular to these notes, we're letting b equal e. Okay. So if we're letting our base equals e, our transformation rules that we're following are f of x equals a times b. Sorry, b is e. I know. I'm broken. Okay. And it's going to be x minus c plus d. Each one of these plays a role, okay? A tells us a story, C tells us a story, and D tells us a story of what's happening with our function. So let's start with D. Your plus D has a couple of roles. It's your vertical translation. If I knew how to spell. It's our vertical translation. It's also our horizontal asymptote. Okay? So whatever the value of D is, that is our horizontal asymptote. That's our boundary line, our no-go zone. Okay? When D is greater than zero, meaning when D is positive, is going to cause our graph to go up, which means that each Y value, we're adding that D amount. When D is less than zero, meaning that D is negative, it's going to cause our graph to shift down, which means to each one of our Y values, we are subtracting D. Okay. Now we're going to go into our C. What we need to remember what C is, X's are liars. Okay. This is our horizontal translation, meaning are we going left or are we going right? Okay. That it got weird. Horizontal translation. So when it says C is greater than 0, what you're really looking at is just C by itself, not the minus, just C by itself. So C being greater than 0, it's going to look like minus C. But it's just a positive C, and it's actually going to be moving to the right, which means to all of your X values, you will be adding whatever C is. Okay. C is less than 0. So C is less than 0. C is going to look like a plus C, but it's actually negative, and you're going to be shifting to the left. So that means to all of your X value, you are subtracting C in order to make it go to the left. Okay. Last but not least is our A. It's our stretch, compression, and reflection. If you go into calculus, this is called our dilation variable. Okay. But for us, it's our stretch, compression, and reflection. And it's all focused on A. Okay. We're not talking about whether A is positive or negative. We're just talking about the absolute value of A. So if the absolute value of A is greater than 1, okay, then that's a vertical stretch. So it's going to be A times your Y. So whatever A is, you're going to multiply by your Y. If A is a fraction between 0 and 1, then that's called a vertical compression or a vertical shrink. So I'm just going to write it as A is a fraction, and I'm still going to be multiplying it times the y. It doesn't mean it's 1 over a. It doesn't mean I want you to divide it. I want you to read it as just letting you know a is a fraction. Okay. And if a is negative, so if a is actually a negative number, then that means you're going to be reflecting across the x-axis. So that means you're multiplying your y by a negative a. So again, each variable has a job to take on, right? Your a is going to either be your stretch or compress, or a reflection, and a reflection. Your c is going to be your liar. X's are liars, but it's telling you whether you're going left or right. And your D is just going to be, simple and easy. You're either going up or down, and it's your horizontal asymptote. All right. So we're going to apply these rules to a problem. So on your paper, you should have the graph of f of x equals negative e to the x minus 3. Do you see this? Yeah. Okay. To transform this, we're going to start with the parent function table. All right. I'm not going to make you graph the parent function, but we're going to start with the parent function table. Okay. The parent function table comes from the values on the front. So on the front where it says parent function, those are the values we're using. Does that make sense? You with me? Okay. So those are our parent function values. I'm going to put up the graph so I can show you that they're the same notes that's on the front of your paper. Got it? I just don't have a front to show you, and I wanted to be able to show you. So I'm going to create a table based on these values. So from here, my parent function, I know that when x is negative 1, 0, 1, and 2, I have the following values. I have 3700ths. I have 1. I have 2 and 7200ths. And I have 7 and 3900ths. Yes? Are these the values on the front of our paper? Yes, Ms. Jones. Okay. So keeping that in mind, now we're going to identify what transformation rules are given to us. You identify the transformation rules by listing out your variables. We have A, we have erase. Our B is E, so there's no point of writing that. We have A, we have C, and we have D. Okay? Your A is your coefficient. So our A equals what right now? What is our A equal? If there's just a negative there, what number is that? Negative 1. Our C is the number with X. And remember, X's are liars. So it looks like it's a negative 3, but it's actually a positive 3. And our D, there's nothing there. So D is just 0. Remember, each one of these pieces has an effect on our parent function, right? So your A is your vertical stretch dilation, your dilation or reflection. Since A is negative, that lets us know that this is a reflection, correct? Yeah. And A affects our Y. So that means we're going to take whatever A is and multiply it times our Y. So each Y is going to be multiplied by negative 1. Our C affects our left and our right. So that means we're taking whatever C is and we're going to add it to our X. So our X is going to be plus 3 because we need it to go to the right. And then our D equals 0. Our D equals 0 lets us know what our horizontal asymptote is. Okay? We normally would go up or down, but we don't need to. But we know that our horizontal asymptote is at y equals 0. That is our boundary line. Okay, so I'm going to make up my new points and then plot them on our graph. So my new points, to every x that I already have, I'm adding 3. So currently my x's are negative 1, 0, 1, and 2. So negative 1 plus 3 gives me everybody. 2. Okay, and then 0 plus 3 gives me 1 plus 3 gives me 2 plus 3 gives me. Okay, now to each one of my y values, I'm multiplying them times negative 1. So negative 1 times all y values. So I have negative 1 times 37 hundredths equals negative 37. So do we see what we're going to do the rest of these? I get now negative 1, negative 2.72, and negative 7 and 39 hundredths. All right. So now I have my new points. I have my new points. I have my horizontal asymptote. Can I create a graph? Okay. So we're going to plot those points. Now, I left your page, your graph without an axis, right? Without an x-axis or horizontal axis. Okay. So you can graph it however you want or however you see fit. When I chose to do this, because all I have are negative y values, I just chose it to graph only in the negatives. Does that make sense? Because what would be the purpose of me having all this positive space if all I'm graphing is a negative? Did you have to do the same thing? No, you can do it however you want. But when I plot my points, I just went ahead and only plotted it there. And then my final shift, I need to move my writing. But this is it negative. So this is me reflected. And then I know that it has to be moved to the right. Does that make sense? So I reflect and then I have to move to the right. So my final graph is going to be this guy, reflected and moved to the right. But you can't see it because I wrote over it. So I'm going to go ahead and erase my writing really quick. So you can see my beautiful graph. Okay. So here are the points that we said we should be at. 1 negative, 3 negative, 4 negative. So are we where we said we would be? I added in the 2. Ignore that one. That was extra. The 1 negative 14. Okay. So when you're doing this, I'm not expecting you to like have the parent function memorized, right? If you can't remember the values of the parent function, can you not just put this in Desmos or a TI-84 and look at a table? Yeah, you can always graph the parent function to get your values of transformation. Does that make sense? So you're not, I'm not saying memorize this, memorize this. No, just know that this is the parent function. You know it's the parent function because there's nothing being multiplied or add to it, right? It's just there. All right, so looking at this, our domain is still negative infinity to positive infinity, but our range has changed. Our range from bottom to top, our bottom is going all the way down to negative infinity, and our top goes up to, where's our asymptote? To 0. This guy is a horizontal asymptote. Okay, so if you have the graph already and all you're doing is moving the points, can you multiply and add? Pretty basic, right? All you're doing is multiplying and adding to make the transformation happen. All right, questions, comments, or concerns about today?